Good morning, afternoon, evening, wherever you are. And as Nikita pointed out, I'll talk about understanding dynamic nuclear polarization and using average Hamiltonian theory to analyze the spin dynamics of this process. So the outline of my talk is going to be, I'll very briefly introduce this time evolution of density matrix and the average Hamiltonian theory. The aim is not here to derive the complete theory. So for those who are interested in it, there are several references. The one I'm using today is this review, this primer by Brinkman here, and I found it extremely helpful. Then I'll discuss three particular cases where we can use average Hamiltonian theory. And the first case will be one electron, one nuclear spin system, and I'll restrict it to only these two mechanisms. There are plenty of other mechanisms that have been proposed and demonstrated. But if you understand these two, and the theory can be extended to others as well. And then this, which we are working on, which is transferring the polarization from NV center, which is spin 1, into a coupled carbon. And then finally, we'll see that if we can use average Hamiltonian theory even to understand cross effect. So very basic, the starting point is that the spin state of a given system can be represented using density matrix or density operator, which is given by this expression here, P being the probability of state psi k. Now, the evolution of this operator will be governed by this Liouville-von-Neumann equation. Most of you are familiar with it. This basically is tells you the state of the system at any given point of time. H here is the Hamiltonian, and that Hamiltonian contains most of the, almost all the information that we can extract, which is internal interactions as well as the interactions that we have control upon, like external magnetic field or radio frequency or microwave radiation. Now, the solution to this equation has typically this kind of form, where U is the time evolution operator. And the key is finding this time evolution operator, which is straightforward if Hamiltonian is time independent. In that case, the time evolution operators look like this. However, the situation becomes slightly tricky if the Hamiltonian has time dependence. And then for that kind of situation, we need advanced theories. Here are two examples I put, but there are different approaches. And one of them is average Hamiltonian theory, which is the focus of today's talk. Now, in the case of time-dependent Hamiltonian, one expansion that helps a lot is the Magnus expansion, which says that the time evolution between time Ta to Tb, if you want to have this evolution operator, the Hamiltonian can be expanded in this form in a series. And the first three terms I have put here for example, and the first term you can see is the average. And you can guess that it's this term that's gives the name of the theory, that is average Hamiltonian theory. So if we can, as later we will see, if we can truncate this series to the first term, which is first order term, right? Then the second order term needs the commutation, and then the third order term, and then it gets more and more complicated. Now, by looking at it, we can directly tell that if the Hamiltonian commutes, if these two parts commute, then there's no need to go any further. The first term is sufficient, and then the time evolution operator becomes, again, simple, the total integration of the Hamiltonian. However, if this does not commute, in that case, we need to make an approximation and truncate the series at some point. And this is called homogeneous in the terminology by Wa and Marik. So we need to do this approximation, and the goal is to make this approximation as good as possible. So the Magnus expansion, it turns out that it will converge rapidly if this norm times time tau is a small quantity. So to achieve this, well, if one can take very small time steps so that this quantity becomes very small, then one can do the numerical simulations with very considering Hamiltonian constant at for very small amount of time. For analytical calculations, one can go into a proper interaction frame, which can improve the interaction. And typically the approach is that if there is, if somehow the Hamiltonian can be broken into two parts, where one part is large and the other part is smaller one, and then it helps to go into the interaction frame of the large Hamiltonian such that the transformed Hamiltonian look like this. And if we solve this equation, it can be written in this form here, where the perturbation part, which is the smaller part, has this transformed form. Now, if further the two parts, H0 and H1, both are, if the both of those are periodic, then one can see that we can write the expression of the time evolution operator in this form, because after every time it repeats, so it's n times. And here this H1 now is the Magnus expansion of this Hamiltonian, which is this smaller part. And you can see that this is the smaller part of the Hamiltonian. And if we expand, then the chances are that the series will truncate later. Like the higher order terms will become less relevant. And if the Hamiltonian is cyclic, then this term is also simple to handle, because you can go n times tau. So simply you multiply. And so these are the conditions we put on the Hamiltonian, that the larger Hamiltonian is cyclic, both the Hamiltonians are periodic, and we go to a frame such that the H1T satisfy this condition. That's it from average Hamiltonian theory. Now I will basically use this framework to understand the spin dynamics. And before I go to the DNP systems, I just wanted to give a glimpse that how can we see, how can analytically the polarization transfer. So here are the matrix forms of operators SG, which are usually, if you go to high magnetic field, and then the polarization, then the state of the system at equilibrium is in Z. All right. So if SG is the initial operator, and suppose we want to transfer the polarization to IG or minus IG, in that case, it will the polarization will be transformed from S to I spin. If you notice carefully that these are density matrices, that the difference is that if you flip, say, these two terms, then you end up here. And on the other hand, if you flip these two terms somehow, then we end up here. So the goal is that somehow can we make an Hamiltonian that takes this as an initial state and evolve it and convert it into this form. Okay. If we see closely, it turns out that if we have these two terms, like as pointed out in this sketch here, if the inner part is called zero quantum basis. So if you have these two terms, which is ix ix zero quantum and iy zero quantum, these terms, one can verify these in MATLAB or your own calculations. Then if we have a linear Hamiltonian, which is a linear combination of these two terms, it will rotate the IZQ part of it, right? And it will definitely flip these two at some point of time. Similarly, the double quantum space looks like this. The basis set look like this. And if we see it closely, just to explain it slightly more, we can write SG as sum of double quantum, which is this part, and zero quantum Z operators. And if we have a pi rotation around Ix, this is just an example, but suppose your Hamiltonian is a total pi rotation and the operator, Hamiltonian operator is Ix double quantum, right? Which is basically this term. Then this will invert the this Iz double quantum to minus double quantum while leaving the zero quantum part unaffected. But now if you see it carefully, then it turns out that this is actually minus Ig. So we started at Sg and ended at minus Ig. So that's how, this is just one example that's how we can transfer the polarization from one spin to another. But so that means the goal is to have the Hamiltonian, which has this kind of form. Okay. Now let's consider the first case, which is one electron, one nuclear spin system. Both are spin half. And S is denoted for electron spins, I is denoted for nuclear spins, and then there are these two, as I said earlier, these two mechanisms that I will be covering. So this is nuclear orientation via electron spin locking, which is called novel. The pulse sequence looks something like this. So the idea is it's very similar to a common cross polarization experiments that we use in solid state NMR. We tilt the polarization, make it coherence, and then spin lock it. The difference here is that we have to repeat this block multiple times, so that because typically in DNP experiments, the number of electron spins are far lower than the number of nuclear spins, so we can pump the system. So we repeat it, and then finally we start detecting the nuclear spins. The other, which is very commonly used DNP mechanism is solid effect, and here it's a pulsed version of solid effect. So basically, instead of continuous pulses, if we have a spin lock pulse only, so the another way of looking at it, if you don't have this first tilt pulse, then the pulse sequence will look like this. And the general understanding of the mechanism is that if you radiate at double quantum or zero quantum transition, then we transfer the polarization. So how do we understand those using average Hamiltonian theory? We have to start from the Hamiltonian. The Hamiltonian looks like this. Okay, so this is the one spin, one electron spin, one nuclear spin Hamiltonian. Here, this part is the microwave irradiation that I showed in the previous slide. This is nuclear Lama frequency, electron Lama frequency, nuclear Lama frequency, and the secular and pseudo-secular term of hyperfine coupling. So these coupling terms, they depend on their relative distances and orientations of the electron and nuclear spins. There are other terms also in the couplings, but we are not considering them. The reason is that we have this, one way to understand that is that if you go to this rotating frame, then the terms that do not commute with SG will rotate with this frequency, which is very large. However, we still consider this term, which is called pseudo-secular term. In fact, this is the key term that drives dynamic nuclear polarization. So in the rotating frame, the Hamiltonian looks like this. So basically, this time dependency is gone because we applied this, and then omega s, which is capital omega s here, which is the offset. So which is the difference in the microwave frequency from the Lama frequency of the electron spins, and the rest of the terms are as they were before. Now, to make it more convenient, it will help if we can combine this SG and SY terms, and then we can do so by going to by tilting the frame a little bit, so that the SG, the new SG prime, becomes in the effective direction of the omega s and omega 1s, right? Now here is the so here we need to understand that these terms, so this omega s, omega naught I, and omega 1s are our controls, right? We can change them because these are affected by external magnetic field and the microwave frequencies and microwave amplitude. The A and B, on the other hand, are the interactions which are part of the system. So either you chemically modify the system, that's how you change it, or you deal with it, whatever we have in the system. Okay, so after tilting, this is the Hamiltonian, and this is simple transformation that this term Sg will become two terms Sg cos theta S by sin theta. Same thing happens here. So this is the very simple algebra here, and then we do go to the frame transformation part. As I discussed in the introduction, we go to the frame of the large interaction, and the large interactions here, there are two large interactions, which is one is rotating with a nuclear alarm frequency, and other one is the effective field, which is the offset and the microwave amplitude, the resultant of the two. So if you go to this frame, the Hamiltonian will take this form, right? This is the taken from the last slide. And here if we look at it closely, this part of the Hamiltonian commutes with both the operators here. That means it will not rotate at all, so it will remain static. The red highlighted part, they both will be affected only by one of the operators. That means they will have only one time dependency. Either they will be modulated by omega s effective, which will be this A term, and or it will be omega naught I term, which is this B term. The last term, on the other hand, will be affected by both of those. So this will have a modulation, a combination of omega s effective, omega naught I effective. So as we know that eventually we are going to take average of it, there is no way that these rate curves will survive, because when we take average and if it is modulating by this frequency or this frequency, the average will turn out to be zero. The static part will remain as it is, so we are considering it. And there is a way that in under certain conditions, this part will survive, will become time independent. Okay, so when we apply this transformation, we get this form here, and we are using cos theta. C theta represents the cos theta, and sin theta represented by s theta here. So it becomes like this. Okay, and here we can already notice that this is like cos omega s and cos omega naught I t. Both are there. So if we rearrange them and just recall, these were our double quantum and zero quantum basis set. If we rearrange them, this turns out to be very nice form, this kind of form. And here it's very convenient, because if we see the double quantum operators, they are modulated by the difference of the two frequencies, while the zero quantum operators are modulated by the sum of the two frequencies. So now if we choose, as I said in the beginning, that these are the interactions that are in our control, because we apply the magnetic field and the microwave frequency. So if we choose those parameters carefully, such that this term becomes zero or this term becomes zero, then some of these terms will become time independent. That means when you take the average of it, it will not be zero. And that is basically in solid state NMR, we call that recoupling. And here, yeah, this term will survive. So the matching condition, so the matching condition here, based on the last expression, will be that when one of these two is zero, right? And we know that omega s effective was a resultant of these two frequencies. So if we consider the case where the microwave amplitude is very small, we see that if that means this omega s is very large than omega 1s, so the matching condition becomes this, which is the solid effect condition. So solid effect conditions, it turns out that it's a special case of this matching. Okay. Then at the matching condition, the Hamiltonian will become very simple form, this as shown here, and the corresponding time evolution operator will be this. Because most the zero quantum terms are zero, because of the fast modulation, and because we are exactly on resonance on condition, the IY term will not survive, because there is sign modulation, sign part becomes zero. It will come back again later on. So if we evolve under this density matrix as Z, as in our initial density matrix, under this time evolution, we get this kind of term. And as we know here that when this cos part becomes -1, then the sign will become zero, and that is when it will become a difference of the zero quantum and double quantum, which is exactly the state we are looking for, that is the nuclear Z operator. So that's when the polarization transfer happen, and that will happen when this factor is pi. So based on that, we can calculate that at this time, the maximum polarization will happen the first time. Okay. So now let's see that if we now do the field frequency profile, that is we vary this omega s. Okay, we vary microwave frequency. When we vary microwave frequency, this omega s will change, and we make sure that at each omega s value we are on resonance. That means we adjust the microwave amplitude accordingly so that this condition is always matched. Then the curve that we get is something like this. Now it has a feature of solid effect, those who are familiar with it, but if you notice, it doesn't go zero in between, it remains there, right? Now, but on the other hand, it's not constant, it's still changing, right? And if you do this kind of term, experiment, which is novel, that if you put first X pulse and then minus Y, the profile looks like this. These are experimental data on Trital. And in this case, when you change the phase of this inverts. So then, according to the theory so far, we are satisfying the matching condition at every point. So one can naively expect that the polarization transfer will be constant throughout, because we are on condition throughout the frequency profile, but it's not the case. And why is that happening? So to understand that, we need to pay attention to the alignment of the magnetization and the spin lock. So these are the spin locking part, and the magnetization that is present right before it, is it actually aligning with it when we are changing the offset? So let's look at that. So to look at that, we can start that in the beginning, we put this pulse. So suppose this X pulse is there. So excitation is omega 1s in X direction, and the offset is omega s in the Z direction. So the effective field is in the XZ plane. So that means at 90-degree pulse, it will basically be rotating in this cone. So it will be 90-degree. The magnetization will be here somewhere, 90-degree on the cone. Okay. Now we apply the next pulse, which is supposing minus Y direction, this case. So and then the effective field will be somewhere this red arrow here, which is in the ZY plane. Now the ZY, this red arrow and that magnetization, they are not aligned. They're necessarily aligned, right? That means this angle, if we find, then we can calculate the projection of M on this omega s effective, which is the cos theta of this angle. If we plot that angle in the three cases, it turns out this kind of profiles. Okay. Now, if we do the powder averaging over it, it turns out like this, and which is closely matching with the novel frequency profile. Now we can use this, and now if we try to do the frequency sweep that we normally do, that is without adjusting at every point, that is the amplitude is constant, then if we vary the frequency, we are deviating from the condition. So we need to go away from the fact that this is always zero, but let's consider this being delta. That means the Hamiltonian will have this form now, because now the cos delta and sin delta both will survive. You see earlier case when delta is equal to zero, that's when this became only the simple form. Now we have to take the average Hamiltonian, because in that case it was constant, now it's time dependent. So now we need to take the average Hamiltonian, and we take the average Hamiltonian, we do the math, it turns out that there is a sinc dependency on this delta, sinc function. Okay. And then correspondingly, we can calculate time evolution operator. That's simple, taking exponential of it. And then we do the evolution under this Hamiltonian. And as I showed previously, we just take the projection. We just calculate this vector, which is how much of the evolved density matrix has IC component into it. And it turns out this. Okay. K here is the scaling factor, which is coming from that alignment factor, that cos theta that I showed previous slide. And then finally, we can take the powder averaging, because this B is the hyperfine coupling, which depends on the crystallite orientation. And this is total final expression. So if we have this expression, now we can plot this expression as a function of time, as a function of any parameter, microwave amplitude or frequency, and check. So here are the experimental result, and here is the analytical simulations. That is the plots generated using that equation. And you can see a remarkable similarities into those. So the theory works out. And one thing that I wanted to point out here, that in general we see that we try to think that higher the power or more the RF microwave amplitude, better the Solid effect. But that's not really the case. If you see here, this green line is 3 megahertz of omega 1s. This line is 15 megahertz of omega 1s, the black one. These two are Solid effect, but with different RF amplitudes. So this was expected that the frequency will shift based on the matching condition, because the matching condition now depends on the, when amplitude is of the order of offset, the matching condition shifts if the amplitude shifts. But you see, both the simulations are showing, because of that scaling, the amplitude goes, the enhancement goes down. Okay, and then there are these features which is not generated in the simulations, because these require additional spin, as Kong later worked on these and solved the mystery that what are those additional peaks that are coming up. Now here there are other three power levels. If we vary the power level, that 5 megahertz, 10 megahertz, and 12 megahertz, you see that as the power increases, less offset is required, because now RF amplitude is large, microwave amplitude is large, and the scaling factor becomes less and less. So at higher power, at low field at least, the Solid effect is not great. The efficiency will go down. Okay. Now we see the build-up curves and we try to simulate those. And here are the four pairs of these values. Okay. So first three pairs, the matching condition is met. The last pair, it does not satisfy the matching condition. When it does not satisfy the matching condition, the build-up curve becomes slow, according to the calculation. However, we did not see that experimentally, and I don't fully understand the reason behind it. But if you see the build-up curves for the other three, when we are on matching condition, so we see that even though at higher microwave amplitude, that the polarization is less, but then the total highest polarization is less, but its build-up rate is faster. So that exactly is the idea, that if you have more RF amplitude, microwave amplitude, the build-up rate will be faster. And that in the high field regime, that actually translates to lower net enhancement, because you get into the competition with the relaxation time. So if the transfer rate is slow, then the relaxation starts to dictate, and then overall the enhancement can go down. But if you turn the relaxations off somehow, for example, in this calculation, then that's not the case. And that can be done in the low magnetic fields, where RF amplitudes actually can satisfy null conditions. So the idea here is that the Solid effect and novel in this regime at least can be considered as the same mechanism, but they flip from, we can switch from one mechanism to another based on whether we are using omega, the offset, to match the condition, or the RF microwave amplitude to match the condition, based on these two. So this is the idea, and that the efficiency depends on two factors, not only on the matching condition or the power, but matching condition and the alignment of the magnetization with the spin lock field. Now the next part is we can now use this same formalism to understand polarization transform from nitrogen vacancy center to neighboring carbon. So because this is now emerging as a promising polarizing agent, and it has applications in quantum sensing as well. So we just wanted to see what happens here. Okay, so the Hamiltonian now is like this. Only difference is that these S operators are spin 1 matrices now, and then the zero field splitting terms comes up. Okay, so again, the first step is the same, because if we are irradiating with microwaves, we go to the rotating frame of microwaves, and then the Hamiltonian become this. So here, this offset terms come, rest of the terms do not change, and this becomes static. So far, so good. Now, the next step here is that we can use a reduced basis formalism. The reduced basis is coming from the fact that we can irradiate near one of the transitions. There are two transitions allowed, 0 to 1 and 0 to -1. But suppose our frequency is near 0 to 1 transition, then we can use these reduced bases to express the Hamiltonian and see what happens there. So you can see that these sigma x, sigma y, sigma z are pseudo spin half. They only depend on two states. Okay, and this term becomes identity in this basis set. So now if we see here, so just to see more closely, this is how sigma x look like. So you see this part of it. This part becomes the Pauli matrices of spin half. Okay, and this part is completely left out because that is -1 state, and we do not do that transition based on the assumption that our microwaves are selective enough, and that is valid assumption because the difference between the two transitions is 2 times omega naught of electron spin, which is large if you go to a decent field, even X band. So then if we rewrite the Hamiltonian in this formalism, this is how it looks like. And the key point here is that these are the terms which is separated, which are -1 state evolved. And here are the pseudo spin half Hamiltonian. And if we look at it closely, it resembles the novel Hamiltonian to a great extent. So here this is written separately after ignoring this part, because that transition is not allowed. So now if you see here, this is sigma g, Iz, and Agg, Agx. These four terms together with this RF irradiation. The difference here is that there is in addition this term coming up, which is looking, the form is nuclear coherence, but it's like as if we apply RF pulse on nuclear spin. And then the Lama frequency has an additional term here, the hyperfine coupling. Right. So with this, if we now do the same thing, but in this case, now we have to do doubly tilted frame. Now we will have to go for doubly tilted frame because now there are Ix and sigma x, both are present. So we rotate in the sigma basis, we rotate with phi, tilt with phi, and here we tilt the calculations by theta using these two operators. And if we tilt, I just want to show the final form here, that if we tilt, the Hamiltonian looks like this. And here these terms BZZ, BXX, BZX, and BXZ, these have these slightly complicated forms. But basically, those are combinations of AZZ and AGX, cos phi, cos theta, sin phi, sin theta. These terms, they make it. The phi and theta are the two tilt angles, which depend on the relative ratio of these hyperfine couplings with the Lama frequencies and the electron offsets. Okay, based on these terms come. So now this Hamiltonian is very similar to novel case. We can again go into these two rotating frame, and we know that when we go into these two rotating frame, only these two term will participate because these two will be modulated by only single frequency, so they will average out. This term will not contribute, but this term will, and we will look into this. And the Hamiltonian, it's exactly same procedure, so the total Hamiltonian will come, average Hamiltonian will turn out to be this, right? And the delta here represents the zero quantum Hamiltonian. So based on this, when we did the simulations, and it turns out that the matching conditions actually now, which we could guess by looking at the Hamiltonian, depend on the hyperfine interactions themselves. So these are the solid effect condition, right? And now if you increase the hyperfine couplings, like here is the ZZ component, and here, so that is A and B in the earlier notation. And these are the simulations. The first column here is X band, and the second column here is 9.4 Tesla. So at 9.4 Tesla, they are like, you can see plus minus 2 omega naught, carbon frequency is 100 megahertz. At X band, it's around 3.5 megahertz. So it's separated by that. And the matching conditions actually depend. If this coupling is too large, there's no polarization transfer. Now, finally, I'll show. So we have tested those numerically also. And if someone is interested, we can discuss later that those results actually match at least with the numerical simulations. Now, final part of it, and I have just this single slide because I think this will convey the point that if we look into the electron-electron nuclear spin system, then the Hamiltonian has this form. And the green part here correspond to the first electron spin, and the yellow part here correspond to the second electron spin, and the hyperfine coupling of the first and electron spins and nuclear spin, second electron spin, nuclear spin, and then the additional part is the electron-electron couplings here. Okay, so there are two parts, exchange and the dipole coupling between two electrons. Now, here the first step would be to go to the basis double quantum, zero quantum, this is zero quantum basis of electrons. So this should not be S here, it should be Z here. So if we do that, we can write this combination just like sum and difference of the two. It turns out that delta is the difference of the two. And if we rewrite, then the Hamiltonian takes this form. And if we take the first these terms here, the two parts, this is sigma part and this is delta part, delta corresponding to zero quantum, sigma corresponding to double quantum, they commute with each other. So they can be treated independently, and then the zero quantum part looks very similar to novel case. And now we can directly predict that based on novel, we know that the matching condition will be the effective field of this SZ coefficient, okay, and Sx, which is these two, with the nuclear Lama frequency, okay. And the polar, so you notice here that if the coupling between the two electron spins is very low, then this is that conventional cross effect condition, because this basically is the difference in the two Lama frequencies of the electron spins, which should be equal to nuclear Lama frequency, right? But if there is coupling present and coupling is large, then this will be the case. And if we see the polarization transfer time, it depends on the difference of the two hyperfine couplings. Okay, delta B comes here. So it does not depend on single, but if the two hyperfine couplings are same, then this will not, the cross effect will not work. So there should be a discrepancy in the two hyperfine couplings. And yeah, the electron-electron coupling, actually, it comes into denominator and here. And then the scaling factor also we can calculate in the same line as we calculated for solid effect and novel. And it turns out that if the coupling is large, electron-electron coupling is large, if this comparable to this difference in the two Lama frequencies, the scaling factor can go down. Okay, so that's all I have, and it's 40 minutes. So I'll take a couple of minutes to thank to the people who with whom I worked in these projects. And the novel and solid effect part was done when I was a postdoc with Bob Griffin, and I was working closely with Jennifer here. And then later on, after joining IIC, I worked with Kong and his postdoc on unifying the all three mechanisms. The reference has been given on the first slide, and the NV's and 13C part is completely idea from my student Shubham, and I want to thank my group as well, and thank you. I will be happy to take questions now.
Thank you so much, Sheetal, for the nice talk. So we are now open for the questions, and you can write your questions in the Q&A sections. Yeah. So we have the questions from audience, and like, what are the advantages of Floquet theory over average Hamiltonian theory?
So average Hamiltonian theory puts those restrictions that the Hamiltonian has to be cyclic and periodic, but Floquet theory works even when those conditions are not met. But of course, that means you go to, and I'm not an expert in Floquet theory, but basically the approach there is that you use this Fourier series and then you go to a Floquet space, which is infinite dimensional. and then you use tricks to truncate that in finite dimensional space. So that way, Floquet theory is more general, even when the periodicity and cyclicity is not met. That's my understanding.
Then we have the next question, and which is like, how is the cycle time defined for novel in NMR, given that the Hamiltonian needs to be cyclic for average Hamiltonian theory?
So it's just like CP, because when the Hamiltonian is constant, and that's the case I took here in novel, so then we can choose a time point when the total rotation becomes 2 pi, and after that it will become 2 pi. So in the constant term, it's simple to take, if I understand correctly. Does that answer the question? Or we can discuss later also.
Yeah, okay. And why is not the off resonance novel sequence maximized at zero offset in the field profile, unlike in simulations?
That's a good observation. It's not maximized. There is slight difference. It's slightly skewed in the experimental time, and I don't have full understanding of it, to be honest. But if I see this is, we are truncating to the first order Hamiltonian. I don't know higher order terms contribute there or not. I don't have the right answer to that. There is some difference. You are right.
Okay, I see. And like, are the pulsed versions, like, can the pulse version be applied for the cross effect DNP?
I think yes. I think so. By the way, in this formalism, there is no role of microwaves in cross effect, because all you need is the. So I did not even consider, if I should have pointed out, I did not even consider the microwave Hamiltonian in the cross effect calculation. But the role of the microwaves in cross effect, according to this theory, is to create the polarization difference which is needed. That's all you can transfer to the nuclear spins. So the role of the the pulse cross effect can be more efficient just because it's more broadbanded, and it will create a larger difference between the two electron spins, larger polarization difference. So I think it has been shown also.
Then, so when we talk about the DNP in the, like, using the NV centers, so which one is more effective for DNP, like the expand or the at 9.4 Tesla, or can we even go lower?
Lower in the field, that's a good question. Lower in the field, we have trouble, and we are thinking about that. But low theory-wise, experimentally, that's easy probably. But the problem is the approximation starts breaking down. That intrinsically, we are assuming that the Lambert interactions are significantly stronger compared to the hyperfine couplings. That's the assumption that H naught is the large part, H1 is the small part, and then we go to the interaction form of the large part. But if that is not valid, then the going to the interaction frame doesn't help, and then the Magnus expansion may not be converging, and that becomes a problem. Expand, it's working fine if we consider the couplings are sufficiently low, that is below 10 megahertz. If we go higher coupling or higher microwave amplitudes, even there we can start having problem. At high field, that problem is not there.
So if you have any more questions, then you can still write in the Q&A sections. I think yeah, most of the questions are, we have taken most of the questions, like all of the questions.
Okay.
So which radical is used in the that cross effect slide which you have shown? Triton.
No. In cross effect, I did not show any experimental data.
Oh.
The experimental data I only showed for novel and solid effect. Cross effect. We did cross effect. There is a paper in where Alisa is the first author. We with Songi, we did it using a dendrimer sample, very interesting dendrimer radical, which is 9 radicals on one molecule, and there we try to understand it.
Okay, great. Thank you. So, yeah, so we have one more question from Lushandra. So for endogenous DNP, where metal cations are used as polarizing agents, which effect occurs? Solid effect or cross effect for polarization transfer?
Depends on the concentration of the metal centers, and of course the dynamics will be much more as I said in NV it's spin 1, so we already have some differences with the solid effect. If there is no metal coupling, metal ion coupling present, the paramagnetic, then it should be solid effect like mechanism. That's the case, but one needs to do the total theory. But then it will be because those spin quantum numbers are not always half, they can be anything, but effect will be single electron spin, single nuclear spin if the concentration is low, and then it will be solid effect kind of effect. If concentration is large, it will be close to cross effect or thermal mixing.
Yeah, I see. So we have question from Blake. So what are the advantages of more spins for cross effect DNP, and how many electrons is too many? 2 electron spins, 3 electron spins, or like 9 electron spins?
That's a good question. This theory is only applied for 2 electron spins on 1 nuclear spin. That's what we did. And if we have more electrons, then the complications in the handling, one needs to be more careful. But one obvious thing is that the stronger the network, then other effects also start to play a role. In I think Asif and others are working on it. The dipolar order start to kick in, and then the spin dynamics changes. So far, this theory in the paper where we worked with 9 radical, it turns out that the relaxation becomes too fast because of these concentrated radicals. So there is not much enhancement. That's what we saw.
So, like, are there any other factors like spin diffusion? Like, how does spin diffusion play a role in this?
In this theory, spin diffusion, or I don't know, spectral diffusion, which one you are talking about, but in this theory, we did not consider, so there's a single nuclear spin. So there's no nuclear spin coupling. So there's no spin diffusion, but it turns out that spin diffusion dictates the overall rate of polar buildup. This is the first step, and the second step is that later on the spins start to get equilibrium, and that nuclear spins, and that happens through spin diffusion process, which is much slower usually, as far as we know, and then that dictates the overall buildup rate. But this does play a crucial role. This is about, like, if we go to higher power regime and if we do pulsed kind of DNP, then it's coherent polarization transfer. I did not consider relaxation in this talk anywhere. So the role of spin diffusion is not that critical, it seems. Yeah.